All right, we're talking inverse functions today, and to get you started, I want you to think a little bit about this problem we have. So there's an American traveler, they're heading to Mexico, and they exchange some US dollars for Mexican pesos. At the time of travel, $1 can be exchanged for 1932 in pesos. At the same time, a Mexican businesswoman who is in the United States is exchanging some Mexican pesos for US dollars at the same exchange rate. So the question is, can we write some equations that relate these two exchanges? So let's think about the first exchange, the businessman who wants to, the traveler who has dollars and wants pesos, right? So let's put dollars into a function. So if they had $1, how many pesos would they get? Well, they get 1932 in pesos, right? So our output is going to be pesos, and our input is going to be dollars. And every dollar we have is going to be multiplied by 1932. And so let's think about the other way, the businesswoman who's in the United States. Now, her output when she gets her money out is going to be dollars, right? She gets dollars out and she inputs pesos, okay? And when she gives them pesos, how much does she get for every dollar? Well, if she had 1932 in pesos, she would get $1. So they take all of the pesos she has and they divide it by 1932, and that's how many dollars she's going to get. So let's think about what's the input of equation 1. The input is dollars, and the output is pesos, right? And then the input of equation 2 is pesos, and outcome dollars. So if I was just standing at the border and I don't know, felt like I had a lot of extra time, I could exchange, right? I could say, here's some dollars and give me pesos. Here's some pesos, give me dollars. And so when I have dollars and I get out pesos, I'm using this equation, right? And so say I have $1,000 and I input it into this equation. I have $1,000, I get out pesos. And then, just for kicks and giggles, I give them that amount in pesos and get out dollars. What am I going to get back? Well, I'm going to get back $1,000. I mean, and this is in a world where there are no exchange fees or anything like that, of course, because we live in these magical, fantastic worlds that don't have things like that. So that's the idea, is that if I input it into this function, I get an output. If I take that output, put it into this function, I get back my original input. So these functions are called inverse functions of each other. They undo each other. So if I start out with $1,000 and I put it into this equation, and then I take that and put it back into this equation, I get out what I started with. So I just undid everything that I started with. I put it through 2 different equations and ended up where I started. It's pretty cool, right? So let's look at what that actually looks like. So you can imagine this. So we have our x. We have some x, imagine this is our dollars, we multiply that number by 2, and then we add 3, and we end up with this function right here, 2x plus 3. Now if we want to find the inverse of that, we want to figure out what equation would get us back to our original x, right? So we take our output, this output of 2x plus 3, we're going to go backwards, we're going to subtract 3, then we're going to divide by 2. So this function right here, y minus 3 divided by 2, is the inverse of 2x plus 3. Because if I put a number into this one, and then took my output and put it into this one, it would give me back what I started with, just like this. So if I put an apple into the function f and get out a banana, if I take that banana and put it into the inverse function, I get back out the apple. So here's some really important notation here. An inverse function has this, this notation that you see right down here, f of -1. So if some function is f of x, then its inverse is f of -1 of x. Now it's super important that you realize that this is not an exponent. So this isn't like f of x to the negative 1, because that really means 1 over f of x, right? And that is absolutely not what we're doing here, because you can see that this function here is not just this function over, or like in the denominator, right? They're not the same. So super important to remember that this f of negative 1 does not equal that, right? It is not. In fact, I'm just gonna I'm gonna erase that so you don't have any idea that that could possibly be the answer, right? F negative 1 just means the inverse, f inverse, okay? So I want you to practice saying that so that you can, keep that in your brain. So let's see what inverse functions really look like. So first we're going to look at them in a table, right? So we know that those two are inverse functions because we know that y minus 3 over 2 undoes 2x plus 3. So let's just do a table of values. We're going to input some numbers and output some numbers, right? Okay, so I'm just going to say when x equals 1, if I put 1 into this, I get 2 plus 3, which is 5. When x equals 2, I get 4 plus 3, which is 7. When x equals 3, I get 6 plus 3, which is 9. And when x equals 4, I get 8 plus 3, which is 11. And when x equals 5, I get 13. And when x equals 6, I get 12, 15. Of course, it's a pattern. That's late, guys. And then 14 plus 3 is 17. Okay, so when I input 7, I get out 17. So now let's see what happens if I put 5 into this function. What happens when I put 5 into it, right? When I take the, let's do this in a different color. When I take the output from here, so I put in apples, and I got out bananas. Now I'm going to take those bananas and I'm going to put them into this function and see what I get out. Well, when I put 5 into here, I get 5 minus 3, which is 2, divided by 2 is 1. When I put 7 in here, I get 7 minus 3, which is 4, divided by 2, which is 2. When I put 9 in here, I get 9 minus 3, which is 6, divided by 2, which is 3. And you can see a pattern here that when I take my output of the other one, it takes me right back to the input of the first one. And so you'll notice that anytime we have inverse functions in a table form, you just take the x and y and you swap them. So basically, if f of x has the point A, B on it, then f inverse of x is going to have the point B, A. So you just switch the x and y to get inverse. So if you had two tables, you could look at them and see, are the x and y's just switched? If they are, then they're inverses of each other. If you want to just find the inverse, all you do is take the x and y from the one table, swap them, and you get the other one. So let's take a look at what it looks like on a graph. So what if we had the function, this is a good one because it's going to come out with something that looks a little different. So we have the function y equals x squared. Okay, so here's the function y equals x squared. It's a parabola. It goes through the points 1, 1, and 2, 1, 2, 3, 4. Ooh, I actually got through that point. 1, 2, 3, 4. Got close there. Okay, so here is the function y equals x squared. And we know that basically what the inverse function is it switches the input and output, right? So our x's become y's and our y's become x's. So let's find some important points here. This point is 0, 0. This point is 1, 1. This point is 2, 4. This point is negative 1, 1. And this point is negative 2, 4. So if it looks like on a graph, all we do is switch the points, right? So our new points are going to be, we're just going to switch the values. So if we switch x and y for this first point, we still get 0, 0. Whoa, what? All right, but then our second point, we're going to switch 1, 1. And what? We still get 1, 1 out? Ah! What happens when we switch 2, 4, though? that time we get out 4, 2. So we go 1, 2, 3, 4 over and up 2. And you see that now we're seeing some differences, right? Now let's switch the point -1, 1. So that one we're going to get 1, -1. Right, so this was 1, 1. This was 2, 4. 4, 2. This one is 1, -1. And then our last point is going to be 4, -2, right? So we're going to go over 4 and down -2. So that's 4, -2. And do you see what happened to this parabola? It got shifted onto its side. It actually reflected over the line y equals x, which I know is really kind of a hard one to see, but it reflects over the line y equals x, and it basically goes sideways. So it reflected over this line right here, and since that line goes through this point and that point, that's why those points stayed the same. But then all of the other ones, if you can imagine just folding your paper over, all of those points just reflected to where they would be if you folded over that line. So that's what it looks like on a graph. Now here's a really interesting thing to think about. Our first one is a function, correct? It passes the vertical line test. Remember, a vertical line test tells us that if I draw a vertical line, that it never touches 2 points of the function at the same time. So our first function is a function. We'll call this f of x. Now the question is, can we call the second one f inverse? Well, is it a function? Well, right here, and right here, and right here, and right here, and in lots of places, it fails the vertical line test, right? I cannot draw a vertical line here without it touching 2 points on my graph. Therefore, this one is not a function at all. So this parabola does not have an inverse function. It has an inverse relation. It has a graph that is its inverse. Absolutely, totally, that is an inverse relation. It has a graph, but it does not have an actual inverse function because it fails the vertical line test. So how could we look at a function regularly and see if it's going to pass the vertical line test once it's inverted, once we find the inverse? Well, if you can think about it, what if this vertical line here would be right here, right? So we have this thing called the horizontal line test, and the horizontal line test tells us if a function fails the horizontal line test, then it doesn't have an inverse. So in other words, if I can draw a horizontal line that touches more than 1 point on the function, then when I take the inverse of this, it's actually not a function. So let's look